Okay, welcome back everyone. In this video, we're going to continue our discussion of electromagnetism by talking about Faraday's law of induction. So the first thing to mention is that this is an empirical law, meaning that Michael Faraday did a bunch of experiments involving electricity and magnetism, and he found the following. This is called the fourth of Maxwell's equations, Faraday's law, and what it does is it calculates an induced EMF or voltage due to a changing magnetic flux. So what he found was that if he took a magnet, just a bar magnet, and he put it into a coil of wire, that it caused a current to flow. And likewise, when he removed it from the wire, that also caused current to flow. And so what we do to calculate Faraday's law is we look at the change in the magnetic flux with respect to time. So EMF equals negative d flux d time, where flux is B dot A, as we talked about previously. Now, one thing that kind of bugged me about this is, okay, how can you have a voltage? So how can you get volts out of a changing flux? So if we look at the units here, changing flux is going to be Webers per second, but Weber is magnetic field times area, which is Tesla times meter squared per second. Now if you think back to when we discussed magnetism, we had the equation F is equal to QVB, which meant that the Tesla was equal to a Newton divided by a Coulomb times a meter per second. So what we can do here is we can solve for Teslas as Newtons times seconds over Coulombs times meters, and we can plug that into here. So we get Newtons seconds times meter squared over Coulomb seconds times meters. So I just rearranged a little bit. Seconds is going to cancel. One factor of meters will cancel, and we're left with Newton meters per Coulomb. Newton meters, you might recognize, is joules, and a joule per Coulomb is the definition of a volt. So this really is a correct equation, even though Faraday came up with this empirically. So how do you get an induced EMF? You have to change one of three things. Because the flux is made up of the magnetic field, the area, and the angle, there's three ways to do this. You can change the magnetic field, you can change the area, or you can change the angle. So really, most of the time the angle is fixed, so we're not going to be looking at that at the moment. So that means that there's two ways to have a changing flux. You can have d flux dt if you have, we'll put a negative sign, if you have a constant area times a changing magnetic field. Or you can have that equal to a constant magnetic field times a changing area. Okay, and we use what's known as Lenz's law to determine the direction of the current that's produced by this potential. Because if we have an EMF produced, that's equal to I times R, Ohm's law, which means that the current is going to be EMF over R. So let's look at a couple of examples of this. And in this lecture, we'll look mainly at how to calculate the magnitude of the EMF, and then in the next part, we'll look at the direction. So we have a loop of radius 16 centimeters and resistance 8.5 ohms, and we want to find the current that's produced at different times below. So we'll write out some of our thoughts. I is going to be equal to EMF over radius, which is 1 over r times negative d flux dt. And in this case, it looks like it's the area which is constant, so we can pull that out. So we have negative a over r, and we will have dB dt. Now, dB dt is just the slope of this graph. So if we calculate the slope at different points, we can find out how much the current is going to be. Now, I've already calculated a over r, and that's about 9.46 times 10 to the minus third, and that's going to be meters squared per ohm. But then when we multiply by the slope, we're going to get current. So that's going to get multiplied by Teslas per second. That's the unit of the slope. So in this first portion here, we are going to have a slope corresponding to basically a fourth. So that means that I is equal to 2.37 milliamps. And even though it's a positive slope, it's going to be a negative current. And we're going to see that negative current typically corresponds to a clockwise current in a loop. And we'll see why that is. In the second portion, the current is simply 0 because the slope here is 0. And in the third portion, this is a slope of about an eighth, right? 0.5 divided by 4. And so that's going to give us a current of 1.18 milliamps. And that's going to be positive, so that will be a counterclockwise current. Okay, so that's one example of how we do this. Let's look at another. So now we have a 50-turn rectangular coil of dimensions 5 by 10, and it's allowed to fall from a position where b equals 0 to a new position where b equals 0.5. We want to find the EMF if this occurs in 0.25 seconds. So for this one, we can just say that the EMF is negative delta flux delta t, which is negative final minus initial over time. And we recognize that flux initial is 0 and flux final is going to be 50 turns times magnetic field times the area. So in other words, each turn or coil of that wire is going to add some more magnetic flux. So that's going to be 50 times 0.5 Tesla. And then we have 5 times 10 to the negative 3 meters squared for the area. 5 times 10 converted to meters. And that's going to give us 0.125 Webers. Okay, so this means that I'm going to have negative 0.125 Webers minus 0 divided by 0.250 seconds. So the magnitude of this is going to be 0.5 volts, but because of that negative sign, like we talked about before, it's going to be a clockwise current. And so we'll talk more about this in the next lecture, where we discuss Lenz's law, which tells us the direction of the induced current that happens as a result of Faraday's law.